This lab, my lab mates were Ariel, Serena, Eleanor, and Brittany, and we explored Kirchhoff's rules. My name is Justin, and I will be presenting the introduction section. Kirchhoff's rules describe how current and voltage behave in electrical circuits based on the laws of conservation of energy and charge. These rules state that energy and current cannot be created or destroyed, but only transferred through different parts of a circuit. The junction rule tells us that the total amount of current entering a junction is the same as the total amount of current leaving it. The loop rule explains that the total amount of voltage gained and lost around any closed path must add up to zero. These laws are important for analyzing and solving complex circuits that can't be simplified with Ohm's law alone, and were first introduced by Gustav Kirchhoff in 1845. Outside of the lab, these principles are constantly applied in real-life systems. For example, a Paso Electric has a power grid that relies on Kirchhoff's rules to balance voltage and current flow across multiple substations through the county. This ensures reliable electricity is delivered throughout the city, especially during those high-demand El Paso summer months. The goal of this experiment was to apply Kirchhoff's rules to a multi-loop circuit, measure the current and voltage across several resistors, and confirm that the conservation of energy and charge works accordingly. By comparing our measured data with theoretical expectations, we can better understand how these fundamental rules keep electrical systems stable and efficient both in the lab and real-world situations. I will now pass it off to Ariel for the materials and methods section.
Hi, I'm Ariel, and this is the materials section of our lab report. First, on our computer, we used Capstone to record our data. This is where we will see our current, and this would be our voltage. We have the multimeter connected here. Then we have 4 different resistors. We put a piece of tape on each one and labeled them with different numbers. Resistor 1, resistor 2, resistor 3, and resistor 4. Then we have different cables. 2 of them are connected to the multimeter, and then the other 2 are connected here. The black cables will be negative and the red cables would be positive. That is all for our materials section. Now we can move on to procedures.
Hello, my name is Sarina Morales, and these are the procedures. To set up Pasco Capstone, make sure the Pasco interface is turned on and the voltage current sensor is plugged into it. On the desktop, open Capstone and drag the digits icon to the center twice. Select current for one box and voltage for the other. In the current box, change amps to milliamps. In the signal generator, change the waveform to DC, set the DC voltage to 7 volts, set the voltage limit to 10, and the current limit to 1.1 amps. Lastly, check the auto box. In this lab, we are finding the voltage and current of different resistors. Voltage can be found by placing the red and black probe that are attached to the current voltage sensor parallel to the resistor. Current, however, will be found using 3 different setups. The first resistor setup to find currents for resistor 1 will have resistor 1 and 2 connected to the voltage current sensor. Resistor 3 is connected between them, and resistor 4 is connected to resistor 3. The black probe from the Pasco interface connects to the end of resistor 4, and the red probe connects to the junction between the resistor 1 and 2. The next setup to find a current for resistor 2 and 3 will have resistor 3 and 2 connected to the sensor. Resistor 1 is the bridge between those 2 resistors, and resistor 4 is connected to resistor 1. Once again, the black probe is connected to the end of resistor 4, while the red probe is connected to the junction of R1 and 2. The last setup is to find the current for resistor 4, which is connected to the sensor this time. Resistor 1 is connected beneath the resistor 4, resistor 2 is connected above resistor 1, so it's on the same level as resistor 4, and resistor 3 is connected to resistor 2 and 4. The red probe is connected to the junction of resistor 1 and 2, and the black probe is also connected to the sensor. Once again, I'm Sarina Morales, and that is all for the procedures.
Now moving on to the data analysis section. In Table 1, the current and voltage values in the circuit for each resistance. In column 1 would be voltage, which is measured in V, and current, which is measured in I. Through the rows, we have resistance 1, resistance 2, resistance 3, resistance 4, and the source E, where we can find the voltage and resistance of resistance 1 would be 4.96, and so on. Source for both voltage would be 7, and the current for the source would be 1.1. Using Kirchhoff's junction rule, the current entering a junction must equal the current leaving it. In our circuit, that means that the current through resistance 1 plus the current through resistance 3 should equal the current through resistance 4. When we add those together, IR1 and IR3, that equals about 19.3, 19.4 milliamps, while the measured IR4 was about 19.9 milliamps. So that gives us about a 3% difference, but showing our data, it actually follows that Kirchhoff's current rule is followed pretty closely. Next, using Kirchhoff's loop rule, the total voltage from the source should equal the sum of all voltage drops. For the first loop, the source of voltage of 7 volts should equal VR1 plus VR4. And when we add those, we get about 6.99 volts, which is about a 2% difference. For the second loop, VR1 should equal VR2 plus VR3. Those add up to 4.97 volts, while VR1 was 4.96, only about a 1% difference. So overall, our results did support both of Kirchhoff's rules with very, very small percent errors. For the extra credit calculations, our results were 1.32%, 0.142%, and 0.201%, all under the allowed limits, meaning our data stayed well within the acceptable accuracy. And that wraps up our data analysis.
Coulomb's Crew Lab Report 5. My name is Brittany, and I'm going to be going over our conclusion for this lab report. Our experimental results overall supported Kirchhoff's rules, confirming that both the junction rule and the loop rule accurately describe how current and voltage behave in electrical circuits. The data collected showed that the total current entering a junction was nearly equal to the total current leaving it, demonstrating the conservation of charge. Likewise, the sum of all voltage gains and drops around each closed loop was approximately zero, validating the conservation of energy in electric circuits. Although small percentage differences appeared when comparing theoretical and experimental values, these discrepancies were within reasonable limits and can be attributed to a combination of factors such as internal resistance in the wires, fluctuations in the power supply, and minor inaccuracies in the multimeter readings. The precision of our results was also influenced by human error, including the slight delays in taking measurements and possible inconsistencies in circuit connections. Environmental factors such as temperature changes that affect resistance may have also contributed to variation in our readings. To minimize these differences in future experiments, the more precise instruments could be used, connections could be double-checked for tightness, and multiple trials could be averaged for improved accuracy. Despite these small sources of error, the experiment provided a clear demonstration of Kirchhoff's laws and helped reinforce the concept that electrical energy is neither created nor destroyed within a closed circuit. This lab not only enhanced our understanding of circuit theory, but also improved our practical skills in data collection, measurement correction, and systematic error analysis. Through this activity, we learned how theoretical physics principles can be applied and verified through hands-on investigation, strengthening our confidence in analyzing more complex electrical systems in future labs. So now I'm going to go ahead and be presenting the diagram labeling explanation. So here presented, you're going to see the same circuit 4 times, where I'm going to be presenting where the sensor in the series will be connected. So for resistor 1, we place the current sensor in series with R1. Meaning it should be connected directly along the path before or after R1, so all current through R1 passes through the sensor. For R2 and R3, because R2 and R3 are in series, they share the same circuit and the same current. You only need one current sensor in that branch, and it can be placed between R2 and R3 or before R2 to represent the entire branch current. For R4, place the current sensor in the wire leading to R4. This measures the total current that flows through the outer branch after the junctions. That's going to be it for our conclusion, and that's going to conclude our lab report 5.